Hello, welcome to this video. Today we're going to find a formula that will do two things. One, we're going to have three parameters, k, s, and t, that represent whole numbers. And when we plug in whole numbers, it will always give us a Pythagorean triple. And furthermore, not only will it always give a Pythagorean triple, it will give you all Pythagorean triples. Any Pythagorean triple you want, there is a arrangement of k, s, and t that are whole numbers that when you plug it in, you get that Pythagorean triple. So first of all, let's quickly talk about what is a Pythagorean triple. It's very simple. So, you were probably at school shown when you learned about the Pythagorean theorem. You were shown some small examples for it, like if you have a right triangle, 3, 4, 5, or maybe the 5, 12, 13. All of these are Pythagorean triples because you can put them on a right triangle like this, and it satisfies the Pythagorean theorem. And they have to be whole numbers. You can't have something like 5.5. You can't have something like 2.5, 6, and 6.5. Although it will work as a squared plus b squared equals c squared, they're not all whole numbers, so that's not going to work. So basically, what we want, A, B, C is a Pythagorean triple if that's right, is A. Is a Pythagorean triple if 1, A, B, and C are whole numbers. So that's just they're from Z, they're whole numbers. 1, 2, 3, 4, or 5, and so on. Or we could go to negatives because we're squaring them. It doesn't matter. And that's the definition I'm going to use of them being whole numbers. So 1, they're whole numbers. 2, they satisfy a squared plus b squared equals c squared. So these are examples of Pythagorean triples, but from this definition, we could also say perhaps -3, 4, 5 is also a Pythagorean triple, as they're all whole numbers, and -3 squared plus 4 squared is 5 squared. So that is a good example. But again, stuff like 1 and 1 give you square root of 2 doesn't work. Although this is satisfied, this is not. So this is not a Pythagorean triple. And something like 2, 3, 4 satisfies this, but does not satisfy this. So stuff like this also doesn't work. But from this definition, yes, we will include negative numbers as well. So now that we got that out of the way, let's do another definition of what we'll call a primitive Pythagorean triple. A primitive Pythagorean triple is basically it satisfies both of these. It's first of all a Pythagorean triple, and it also satisfies that the GCD of A, B, and C is 1. So if this is happening with both of these, then that does work. And we can see that we can get every Pythagorean triple from just the primitive ones. Because if we have a Pythagorean triple, so we have our a squared plus b squared equals c squared. It's just a general Pythagorean triple. Then, if we say, well, let's call their GCD of A, B, and C D. The biggest number that divides all three of them. So now here we'll be able to divide by D squared, and we'll get A over D squared plus B over D squared equals C over D squared. And because D is the biggest number that divides A and B and C, that means that the GCD of A over D, B over D, and C over D has to be 1. And because D divides into A, B, and C, because that's just a definition of GCD, it's a requirement. We know that these three are whole numbers. Of course, we just saw they satisfy this equation, and their GCD is 1. So this is a primitive Pythagorean triple. And so all we need to do to get any Pythagorean triple is just go to the primitive one, and that is just dividing the GCD of the three numbers squared by that equation. So let's look at an example. 6 squared plus 8 squared equals 10 squared is not a primitive Pythagorean triple, but it's still a Pythagorean triple, and we can get the origin of it, the origin of this Pythagorean triple, by dividing by the GCD of these three numbers, and when we divide the GCD squared, and so when we divide by 2 squared, we get 3 squared plus 4 squared equals 5 squared. And we know this is a Pythagorean triple, it has to be. And it's also a primitive one, just like we expected. And so, now we know all Pythagorean triples are basically a constant multiplied by a primitive Pythagorean triple. So now, let's look at a primitive Pythagorean triples and find a formula for them. And then all we'll have to do is multiply each one of A, B, and C by K to get any general Pythagorean triple. So let's erase the board and do that. Okay, now let's look at a primitive Pythagorean triple. So we know A, B, and C are from Z, A squared plus B squared equals C squared, and their GCD is A, B, and C. Of A, B, and C is 1. That's the GCD. And we want to find a formula that when we plug in any whole numbers, we will get a primitive Pythagorean triple, and we'll get also every primitive Pythagorean triple. So we'll start from just the complete generalized, only the exact definition of a primitive Pythagorean triple, and we'll work out that there exist constants t and s, such that when we plug in, there exists constant t and s, that each one of them represents a certain function of t and s, and we'll get a Pythagorean triple that from what we did we'll know will give us every primitive one, because this is just the this is the most generalized form of a primitive Pythagorean triple. Now let's begin. So first of all, let's not rearrange this equation. Let's look at the possibilities we have for even and odd in A, B, and C. So we have four options. Either A is even, B is even, and in turn, because of even plus even equals, has to be even, C squared will be even, and so C squared would be even, so C would be even. But that's already out of the picture, as this is not a primitive. They're all divisible by 2. So the GCD would have to be at least 2. If we look at A is odd and B is odd, then we get that again C is even. At first it seems to be able to satisfy all the rules, but let's actually take x, y, and z, and such that A is 2x plus 1, B is 2y plus 1, and C is 2z, and we'll look at it mod 4 instead of mod 2. So if A is odd, it can be represented as 2x plus 1, and then that squared plus a b. And if b is odd, it can be represented as 2y plus 1. And yes, obviously x and y are whole numbers. And b squared, so that's a squared plus b squared, that's c squared. And because c has to be even, because these two are odd, let's write it as 2z. Let's write it as 2z, and that is squared. So that's a squared plus b squared is c squared. If we expand this out, we get 4x squared plus 4x plus 1 plus 4y squared plus 4y plus 1 is 4z squared. Now we can see that there are a bunch of 4's here that are multiplied by whole numbers. So 4 times x squared, 4 times x, y squared, y, and z squared. And so it's basically this 1 plus 1, and it's all surrounded by noise that is divisible by 4. So if we do this mod 4, we know that all of these 4's would become zeros. And so mod 4, we get 1 plus 1, which is 2, is congruent to, so this is this side, mod 4. These disappear, we get 1 plus 1, which is 2. It's congruent to this side, mod 4, which is 0. So this is 2 is 0 mod 4. And that is obviously incorrect. And so this is also impossible. So now, let's look Okay, so now let's look at the other two possibilities that we have. Either A is odd and B is even, in which case odd plus even will give us C is odd, or it's the other case where A is even and B is odd, and so we'll get that C is odd. Now you can think about these, but you'll get no contradiction when playing around with these. And that is to be expected, because these are basically the same case. We just switch between the A and the B. And because of the symmetry between A and B here, these are pretty much the same case. And so if we got a contradiction in one of these cases, then we would get a contradiction automatically in the other because of the symmetry between A and B. And so we would get that there are no primitive Pythagorean triples, which would be a contradiction to the fact that 3 squared plus 4 squared equals 5 squared exists. And so so we know that these two can be wrong, so these have to work. But now we have two cases to choose from, and we don't have one easy case to just work with this. Except we do, because just like I said before, switching the A and the B, replacing A with B and B with A, does not change any of these conditions, and also will give us that this case is actually pretty much the exact same as this case. And so we'll be able to say that without loss of generality, we will look at the case where A is even, B is odd, and C is odd. So let's now erase this and now work with this assumption. بود קוד יאללה. התחלת?
כן.
למה זה לא... אתה ראית שאני מדבר לעצמי פה? Okay, now that we've established that without loss of generality, this is the case that we have, let's work with it. So now let's play around a bit with our equation. A squared plus B squared equals C squared. Well, we know that maybe factoring could help us here, but there is no factoring, at least not with real numbers and sums of squares, but there is with difference of squares. And how do we make that happen? Very easily. We'll subtract b squared from both sides. So we'll get a squared is equal to c squared minus b squared, which is c minus b multiplied by c plus b. Now we know if we can get that these two are perhaps co-prime, that means that we'll be able to use the fundamental theorem of arithmetic, which is every number that's at least 2 can be represented uniquely as a product of powers of primes, and we'll be able to say that they have to be square numbers. And so this is the basic idea behind trying to prove that these two are co-prime, aka their GCD is 1. And so let's actually do it a bit more formally and a bit more just a bit better. So we want to show, well, first of all, these sadly can't be co-prime, as because C and B are odd, these two are even. But maybe if we show that the biggest common divisor, and that not only 2 divides both of these, but it's the biggest one that divides both of them, we'll be able to perhaps divide by 4 and still be able to use what we wanted to use. So our goal now is to prove that the GCD of C minus B and C plus B is 2. No more, no less. Exactly 2. So how are we gonna go about this? Well, first of all, we'll be able to realize, just like I said before, these two are even because C and B are odd. Meaning that if these two are even, 2 has to divide the GCD of C minus B and C plus B. And so, this means that we can represent the GCD of C minus B and C plus B as 2 times D. And we get, if their GCD is 2 times D, that means, obviously, because it's the GCD, because 2D is the GCD between C minus B and C plus B, we know that 2D divides C minus B and at the same time divides C plus B. Now, because these two divide 2D, we can sum them up. We can sum them and subtract them. If we sum them, we get 2D divides 2C. And if we subtract this from this, we get 2D divides 2B. Now, in cases like this, we can obviously remove the 2. So we can sort of cancel out the 2. And we get the D divides C and D divides B. Now at first it doesn't seem like a problem because it could just be the case that A does not divide D and their GCD is still 1 and it's still a primitive Pythagorean triple, but that is not the case. Very simply because this A squared is C minus B times C plus B. If 2D divides C minus B and 2D divides C plus B, then it has to be the case that 4D squared divides their product. So 4D squared divides C minus B times C plus B, which just so happens to be A squared. And 4D squared is 2D squared. And so we get if we know something squared divides into another thing squared, then we can sort of do a square root on both sides and remove the squares. Again, I think by pretty much just using, again, by the fundamental theorem of arithmetic of multiplying primes, and where do all the primes in 2D have to go? If they don't go in A, 4D squared can't possibly divide into A squared. And so from this we can say 2D divides into A. But that means if 2D divides into A, obviously D divides into A. And we get a contradiction. Because D divides C, D divides B, and D divides A. And so the GCD of A, B, and C has to be at least D. Now this is not a contradiction, because D can still be 1. But we get so that the GCD of A, B, and C, which is 1, has to be bigger than or equal to D. Or D divides 1, or however you want to write it. But because D has to be this whole, or has to be this natural number to divide C minus B and C plus B, we know that D is also bigger than or equal to 1. If D is smaller than or equal to 1, bigger than or equal to 1, D must be 1. And so we get that the GCD of C minus B and C plus B is 2 times D, which is 2. So now, this is not an assumption, this is a fact. And now, let's quickly erase all of this and look at the consequences of this on our equation. Okay, now let's continue. So now we know that the GCD of C minus B and C plus B is not just at least 2 or is divisible by 2, it is exactly precisely 2. So now, just by properties of GCD, we know that it has to be the case that the GCD of C minus B over 2 and C plus B over 2 is 1. Basically meaning C minus B over 2 and C plus B over 2 are co-prime. Now, we want to use this in this product, but here we just have C minus B and C plus B, not this over 2 and this over 2. But this can easily be fixed by just dividing by 4. And so we'll get A over 2 all squared is C minus B divided by 2 times C plus B divided by 2. And now this is gonna look a tiny bit ugly with the products, but I'll make sense of it intuitively. So now we'll properly use the fundamental theorem of arithmetic that says any natural number that's at least 2. So I also should have mentioned, yes, in the primitive one, I should have mentioned it does have to be the case that these are natural numbers. But to get all the Pythagorean triples like negative A, B, and C, you'll be able to see how we'll be able to fix that in our complete theorem, in our complete formula, not theorem. So if n is a natural number, n is at least 2, we know that n can be represented as a product of powers of primes. So p to the a. So we have p1 to the m1 times p2 to the n2, so on until pk to the mk. And every pi, each one of those p's represents a prime, and each one of those powers is just a power that's at least 1. And we also know this, it's not just it can be represented this way, it is uniquely represented this way. This is unique. You can find something like 2 squared times 3 is the same as 5 times 7, or things like that. You won't be able to find different ways to represent a natural number that's at least 2 as a product of powers of primes. It won't happen. Distinct primes, I should say, also. P1, P2 up until Pk also should be different. But the powers can be the same, it does not matter. So now let's use this. So let's say C minus B over 2. Let's say here c minus b over 2 is p1 to the m1 up until pk to the nk, and let's say c plus b over 2 is q1 to the n1 up until qr to the nr. All of the, so yes, it does look a bit ugly, but the product of these is a over 2 squared. And so if we say a over 2 is if we say a over 2 is something like t to the v, t1 to the v1 times all the way up to tu to the power of vu, then we get that this thing squared is this times this. Now, we know because of this, these are all distinct. P1 and PK are all different in themselves, by themselves, but they're also different than Q1 until QR, because their GCD of C minus B over 2 and C plus B over 2 is 1. And so I know these are distinct primes, and the product is equal to this thing squared. And by the fundamental theorem of arithmetic, there has to be one unique way to represent a over 2 all squared. One way is this thing squared, which will double each power. And one way is the product of these two. And because all the primes here are distinct by this GCD, we know this is a proper way to represent a over 2 all squared as a product of powers of distinct primes. And so these two ways, this times this and this, have to be the same. All the primes should have to be the same in any order, and better yet, all the powers have to be the same. Which means 2v1 up until 2vu have to represent m1 until mk and n1 until nr. Now remember, the powers are natural numbers, at least one, meaning that these are even natural numbers. And because each one of them represents exactly one power between m1, mk, and n1 till nr, we know each one of these, m1 till mk, n1 till nr, has to be even. And if they're even, we can represent them as 2x1 and up until 2xk, 2y1 up until 2yr. And then we'll be able to factor 2 out of everything. And we'll be able to say c minus b over 2 is something squared. So, so we'll be able to say this is something like 2x1 up until 2xk. This, so instead of this, we'll be able to write this. Instead of this, we'll be able to write 2yr. Instead of this, 2y1. And all of the powers that are even, meaning that this, when we factor out a 2 from all of these products, it's a product of p1 to the x1 up until pk to the xk, all of it squared. And we know, and p1 to the x1 up until pk to the xk has to be a natural number, as p1 and pk are themselves primes, and so natural numbers, products of natural numbers is a natural number. And so we know this is a natural number. We'll call it s squared. And the same thing applies to c plus b over 2. It is t squared. So this this is the hardest part to understand from this proof, so I'll quickly reiterate it. From the fundamental theorem of arithmetic. So first of all, because these are natural numbers, from this, we can use the fundamental theorem of arithmetic to write c minus b over 2 and c plus b over 2 as a product of powers of primes, like this. And because the GCD is 1, not only are all of p's and q's distinct by themselves, they're also distinct between each other. If c minus b divided by 2 is divisible by 2, if say p1 is 2, then none of q's of the q1 up until qr, neither of them can be 2. And their product is a over 2 squared, and a over 2, again, is a natural number by the fundamental theorem of arithmetic. It is another product of primes, of a product of powers of distinct primes. And when we square it, all we do is multiply each of the powers by 2. Now, when we multiply these, we get this. But we know that these primes are different, and so this is a proper way to represent a over 2 all squared as a product of powers of distinct primes. But from the fundamental theorem of arithmetic, we know there has to be exactly one way to represent it. And so we know if we get 2 ways, they have to be the exact same. All the primes have to be the same, all the powers have to be the same. And so we're going to focus on all the powers have to be the same. Because that means that all of these even powers, 2 times something, are distributed between all of these. And so we know all of these powers are even. If we take a 2 out of all of this, we get c minus b over 2 is something squared, which we'll call s squared. And similarly with c plus b over 2, we get that it's something squared like t. c plus b over 2 is t squared, whereas s and t are natural numbers. Okay, now we know, now that we know this, now you can also see easily, now, you can also see why, if s and t are co-prime, then you will easily get the exact same thing, and you will be able to trace everything back and get that that it will represent a primitive Pythagorean triple. And so you can see for all s squared and t squared that we plug in, it will apply. This will be a primitive Pythagorean triple, again by all the work we did. We'll just do it backwards, and we'll get this. And so now that we know this, we can individually find c, b, and a in terms of s and t. And so let's first of all get c and b out of the way. The sum of these two, c plus b over 2 and c minus b over 2, the sum of them is clearly c. So c is this plus this, which is s squared plus t squared. B is c plus b over 2 minus c minus b over 2. And so b is t squared minus s squared. And when we plug in c minus b over 2 and c plus b over 2 here, we get, let's do it on the side, a over 2 squared is s times t all squared. We can cancel these squares out and multiply by 2 to get that a is 2 times s times t. And so for t and s that are co-prime, we get that this gives all primitive Pythagorean triples, because, like I said at the beginning, we started from the complete general primitive Pythagorean triple, and we got that it has to equal this for S and T natural numbers that are co-prime. And so plugging in all natural numbers should give you plugging in S and T as co-prime natural numbers should give you all primitive Pythagorean triples, as all of them have to be able to be represented this way. And you can also see algebraically, if you square this and square this, their sum will always equal this, which also is cool to see the algebra in work. Okay, now that we have a formula for the primitive Pythagorean triples for all of them, just by substituting in co-prime natural numbers S and T into here, and T does need to be bigger than S for them to be natural numbers, for B to be a natural number. But now we know every Pythagorean triple is just some number. So A of a general Pythagorean triple is just a certain number K times an A that is in a primitive Pythagorean triple that represents a number in the primitive Pythagorean triple. And so if we multiply each of those by a whole number K, so K times C, K times B, K times A, we get that we're multiplying these by K, for K is a whole number, we get every Pythagorean triple, pretty much. But you see, S squared plus S and T have to be co-prime in this, and T has to be bigger than S for it. But I don't want to get into that. And so to allow A and B to be negative numbers, and also C to be negative with the K, I will let S and T to just be whole numbers, not have to be natural numbers. And also, because S and T and so because S and T actually don't have to be co-prime also for this to represent a Pythagorean triple. All we need S and T to be are whole numbers, because it's if we have S and T say are divisible both by 2, then it would be the same as taking a primitive one that is just all of these divided by 4 and then multiplying them by 4K. It won't change a single thing if we just say S and T, first of all, are whole numbers and not natural, to allow A and B to also be negative, and without the restriction of T being bigger than S. We'll also allow K to be a whole number, so C can be negative. And so now we get A, B, and C can all be positive, negative, or 0 if S or T are 0 in certain cases. And we get also just every case, also the ones with negative numbers. And S and T also don't have to be stuff like co-prime, because just as we discussed, it won't change a thing. The triple will still be something times a primitive Pythagorean triple, which is which is just a bit smaller, which is smaller numbers than s squared t squared into st by a certain constant. And so finally we get that for s, t, and k that are whole numbers, we get that all triples of the form all triples of the form 2 k st k times t squared minus s squared and k times t squared plus s squared, we get that all of these, we get that when we substitute all of the whole numbers into this, we'll get all of the, when we substitute in all the whole numbers, we'll get all the Pythagorean triples, and when we substitute in, any just whole numbers that you choose, s, t, and k, you will certainly have to get a Pythagorean triple. It's not that it's occasionally, it will always give a Pythagorean triple, and it will give you all Pythagorean triples depending on which s, t, and k you choose to substitute in. And finally, that's it. If you want more content like this, please subscribe to my channel. I'll be uploading more interesting things like this in the future. And finally, that's it.